So I'm going to do an introduction to Imagenet and also something connected to Imagenet called the ILSVRC, which is the Large-Scale Image Recognition Challenge, which has driven a lot of research in computer vision, particularly convolutional neural nets. We'll explore two of those architectures, one of them in particular. Then we'll look at a paper called Decaf, which has also been the catalyst of a lot of research into transfer learning, the topic at hand. We'll look at some of the benchmarks that the Decaf paper goes through on different data sets, which explore the viability of this thing called transfer learning. Then we'll look at an interesting topic called fine-tuning, which is in the kind of the transfer learning realm of technologies. And then I think most interestingly at the end, so we're going to go through these first sections real fast, and at the end we'll spend hopefully the bulk of the time looking at some actual case studies, and we'll actually fine-tune a convolutional net on a novel data set for sentiment analysis. So let's jump right into it, and quick intro to Imagenet. So Imagenet's a project that has been taken on the big task of essentially human annotating images, because we all know if we work in supervised learning that we need data. Someone's got to label it. Usually it's a human. Usually it's crowdsourced. This is a giant crowdsourcing project that's labeled definitely over 1 million images, but for the contest, the ILSVRC, we use a collection, a sample of 1.2 million images, and we try and learn to predict 1,000 class labels. So you can kind of see a quick collage of different images here. They're typically objects with hopefully one focal point for the task of image classification. So there's dogs, cats, people, bikes, any number of objects you can think of, thousands of categories, and there's a whole hierarchy. They're categorized too. So lots of different applications. ILSVRC contest, once again, just takes a subsample of that over 1,000 classes, and the goal is to make the best classifier you can do. And the common way to do that nowadays is through deep convolutional neural nets. The most popular one came out in, I think, 2012. It's called AlexNet. It came from Hinton, who kind of had Hinton and his group over there in Canada. But basically, it wasn't the first architecture to use convolutions, but it was the first one to start going deep. So here in this top diagram, let me get my pointer ready. You can see here's the input image. Here's the first convolution, the second convolution. 2 convolutions were done before this, but they did 5 convolutions. And then the standard fully connected layers at the end. 2012, that was kind of groundbreaking on Imagenet. It blew away everyone away by like 20% accuracy. Nowadays, this is Inception on the bottom. This is state of the art. And it's just kind of insane how deep it is and complicated it is. And it uses something called deception modules, which does work in parallel. So lots of different trade-offs with the technologies. This is kind of the one that really spurred all of the research, AlexNet. And we'll evaluate the merits of it through different case studies. And particularly, we're going to look at this fully connected layer here. I labeled it FC7. We'll look at FC6 too. We'll look at those and figure out what comes out of those. And the purpose of this transfer learning talk is that we want to leverage work that's already been done, and I want to motivate you to not train a classifier on Imagenet. To make these convolutional architectures work, you need a lot of data per class, generally, in my experience, at least 1,000 images per class. And these fully connected layers here, they're very big matrix multiplies, so there's a lot of computational overhead on those, especially if you're not using GPUs. In my experience, you can do about a 1.7 images per second. That dot's not supposed to be there. But you could do 1.6 images per second on backprop. So that's kind of throughput I see on my commodity hardware with the GPU. There's also incentive to try and train Imagenet as fast as you can. So there's a table here which kind of summarizes that. And this is a funny tweet I saw that came out within the last month. There was a group in Berkeley who had a $1 million budget to train Imagenet as fast as they could. So and the quote goes, "Our hardware budget is only 1.2 million, which is 3 times lower than Facebook's 4.1 million." So with that budget, they were able to train Imagenet in 24 hours. But for people like us, maybe hobbyists who have just commodity hardware, maybe 1 GPU on AWS, it'll be on the magnitude of about 2 weeks in general. So not a lot of, incentive to do it on your own, unless you want to waste a lot of electricity and money, when most architectures, most frameworks have these models pre-trained, ready for you to use. For example, if you use Keras, if you use TensorFlow, if you use Caffe, if you use Theano, all the big frameworks have pre-trained models for you to use. So some use cases for transfer learning that we can look at are just plain feature extractors, which we're not doing any training on the neural net on that. We'll look at fine tuning, which is what we do a little backprop on. And then we'll also look at just using the pre-trained models. So those are some use cases we're going to explore. And like I mentioned, a lot of these benchmarks come from this Decaf paper. I encourage you to all check that out if you want to explore the merits of these deep learning techniques. So here's the first kind of look at these convolutional features and the motivation behind deep learning. This picture on the bottom is an excerpt from the Decaf paper, and it looks at the Imagenet data set fed through a pre-trained AlexNet architecture. And as you can see here on these last two, these are the image features taken from the first convolutional layer, and this is the scatter plot of the features taken out of the first fully connected layer. And as you can see here, in this connected layer, there is some structure here. For example, these class labels are structure, commodity, conveyance, invertebrate, bird, hunting dog. So this is a subset of the Imagenet classes. We fed these images with that label through this network, but we didn't go all the way through. We took it out here. We have a 4,096 dimensional feature vector, and then we plotted it in 2D, and you can see that there is some semantic structure there. The classes are separable. Now compare that to earlier in the network. After the first convolution, there isn't much semantic structure there, at least projected down into 2D. Just a second, David. And this is also contrasted with some handmade features here from different, kind of before the convolutional idea came out. We do feature engineering often, and these are some engineered features, and you can see there is some clustering there, not as good as we get from the pre-trained network for free. David, do you have a quick question?
Yeah, the question is, how did you plot in 2D?
TSNE is a good way to do it.
Okay.
Yeah.
Thank you.
Mm-hmm. And that's what this is. So yeah, the main point here is that we can get semantic structure from the network through the later layers. So we can use the 6th fully connected layer or even the 7th, and we'll look at that more onto different data sets. So this is an example of feeding object examples through Imagenet. Now we'll look at more evaluation. So now we're going to look at a different data set and see if a pre-trained network on Imagenet transfers to a different data set. So we trained on Imagenet, now we're going to evaluate on Caltech 101. This is a data set. It looks like it's in the same vein of Imagenet. It has different, it's just like objects, it looks like, simple things. They look very clean though, maybe curated a little better. But let's see if, in theory, I think this should work. Let's evaluate. And there's 9,000 images, and it's also, there's a different number of classes. There are only 101 classes in this data set. So here's some evaluation metrics that come out of it, and some interesting things we'll discuss. So we pulled features out of the last convolutional layer after the polling. We pulled them out of the first fully connected layer, and we pulled it out of the last fully connected layer. And so we got those image features out, and then we fit a logistic regression and an SVM to it. And as you can, and also we compared to a baseline here, which are handcrafted features. And this last one that is covered up right now is a convolutional net, but it's only 2 layers deep. And once that goes away, you can see that it didn't do very well, and that's maybe a kind of a comment that deeper is better. We got 5 convolutions here versus 2 convolutions, and the results are much better. 65 up to 80. So as you can see, we got the best results using an SVM. The SVM versus logistic regression was a bit irrelevant in this case, but we do get the best results from this FC6 here. And just for reference, I guess if you have 100 classes, the random baseline is less than 1%. So we're doing a lot better than that. We're doing 86%. And also an interesting thing in this Caltech data set is that the class distribution is very imbalanced. A lot of the classes, for example, a dog class versus a car class, they're not all at 50%. They're not all equal. So the results here really shine. Because we're already building on a foundation of a well-trained Imagenet network, the class imbalance doesn't really come into effect. I don't have a cluster, I don't have a confusion matrix here to prove it, but the overall accuracy is looking good. Also, another really interesting thing from this Caltech evaluation here is in this plot right here. What it does is it shows the accuracy of our logistic regression and our SVM per the number of training categories. So if I take one Caltech 101 image and and try and classify it, I'm able to get accuracy already. If I take 5, it goes up to 60%. If I take 10, it goes up to 80%. And as I can see here from these handcrafted features, I can't get results until 60%. So I think that's pretty compelling results there, that we can do something called one-shot learning, leveraging a pre-trained model. You know, gathering data is often difficult, especially labeled data. In this case, we don't need a lot. We can get results with small class samples. Here's another data set we'll look at to look at the merits of transfer learning. This is the office data set. It's a collection of different shots around an office. So one of them is with a DSLR camera, one of them is with a webcam, and another one is from Amazon. And as you can see here on the right, this is the TSNE projection again of the features fed through the Imagenet architecture. You can see here that all of the scissor images from the different data sets, so the green one is from the office data set, and the blue one is from the Amazon data set. You can see that they're clustered together. So these two different data sets are from different domains. Imagenet's very close-up centered. This office one is very skewed, very changed. There's different aspect ratios. So that shows that the Imagenet trained model can achieve some type of domain adaptation and learn and get information from data sets that it wasn't even trained on. And compared here to this handmade feature extractor, where, for example, this cup and these scissors are clustered together. And it also clusters scissors up here too, so that it's not getting as much semantic hierarchy that we would expect. Another interesting data set to look at, we're going to fly through these and look at some actual code in a bit, so let's just get through these to explore the...
Sorry, Alex. The handmade is using normal convention image analysis, image processing algorithms? Or?
Yeah, it's not using deep convolutional networks, yeah. Okay. So handmade features, I don't know the exact details. We're just looking at a few baselines, yeah.
Okay, thank you.
Pre-deep convolutional network techniques. Here's a Sun database. This one, data. So this is of not objects, it's of scenes. So let's see if we can adapt to this data set. We have 130 images, 397 classes. And we took a sample of some of the class labels. We have outdoor man-made, outdoor both, indoor. So we have indoor and outdoor. We're going to feed that through the Imagenet architecture, take out the activations at the fully connected layer 6, plot them into 2 dimensions in TSNE, and you can see there's clustering there. So in this case, we had a model that was trained on objects, but it was still able to take out semantic structure from a data set of scenes with no focal point in them. So, and that's pretty compelling results there for the merits of transfer learning on different data sets. And here's of the same example of the scene recognition where we try to fit a classifier to it, where random guessing baseline would be less than 1% accuracy, and we get up to 40% here with a logistic regression, and compared to 38% on the handmade features. And it's also interesting too to kind of figure out, you know, which fully connected layer is better. It seems like most of the time on this architecture, the first fully connected layer has some advantage, but not much. And as we go deeper in the network, you know, over here these features might be very basic. Maybe this is edges, maybe this is shapes, and it's hard to quantify what the model learns as it goes through the convolutions. But as we go on, the features become more specific. So there seems to be a little advantage of using a more general representation, and I think that makes sense because the data we're feeding through it has nothing to do with the data it was trained on. So it seems like the further back in the model you go, the better results you get, and we could see that here. Now here's the interesting things I want to show you, some case studies. We're going to look at something I showed in my last talk, which I used before. It was on the Amazon data set, where we pass Amazon images, something completely different, into Imagenet, and see if they can learn some structure from that. And then we're going to look at an example of image sentiment analysis using feature extraction and fine-tuning, so 2 parts of that. And then we're actually going to train a classifier on that, a VGG CNN. And then we'll look at an Expedia example. And we'll look at something Google did recently, a cool project where we'll do a live fine-tuning example. So a lot to cover. And this is a nice diagram. I forgot to put the attribution on here, but this is from Karpathy, one of his lectures. And it shows, it's a nice visual example of fine-tuning. So this first image here is just the standard convolutional neural net stack. We have the convolutional layers followed by the max pooling at the end and the fully connected. However, here we have an example of feature extraction. So this is something you do when you pass the images through and you just want that 4096 dimensional feature vector, something that describes this image, something I could work with. However, there's the third case of what we want to do sometimes is where we do fine tuning. That's where you train half of your network or the end of it on your new data set. So that has advantages because the work that's already been done, this model's been trained on $1 million of electricity in some period of time. It's already initialized our weights for us. And now we just want to fine tune the last bit of them on our novel training set. So that's something we could do with fine tuning and we'll explore. So here's my example of Amazon. A lot of you have already seen this. It's what I did my grad work in. But we fed Amazon images through the AlexNet architecture, pulled out the features on the last fully connected layer, plotted them in 2 dimensions, and you can see there is semantic clustering. This is no clustering algorithm. It just comes out of there like that. All of the things are grouped together. So you could easily train a linear classifier on that if you want to. We actually didn't use that. Our use case was to use these image features in a recommender system and to help us with the cold start problem on recommenders. So just not getting into this, but you can see we got really good results on this cold start problem. We got 30%, up to 25% here, and 30% on non-visual items too. So real useful information you can pull out of these images using convolutional neural nets. Now this next example I want to talk about is called image sentiment analysis. It's something I'm working on currently. So there is a data set that was curated a little bit ago called the Deep Scent data set. And it's pictures taken from Twitter, and they crowdsourced the labels. So you probably can't see here, but above these images, you can see there's a 1 and there's a 0. So that's negative sentiment, positive sentiment. So I wanted to do an experiment to see 2 things. If I could get those feature vectors out, and if the Imagenet architecture can generalize them well enough to train a linear classifier on it. And then the next experiment was to do fine tuning on it. So this first one, I have a notebook we can look at. And I'll move this. And I'll make the text bigger. I can't. Okay, so I'm loading my data set from disk, and now looking at a bunch of code on a screen isn't that fun, but just bear with me. So we're just loading this Deep Scent data set from disk. It's a folder full of those images I showed you in the presentation. Here I'm setting my batch size for feed forward to the network. This is boilerplate for TensorFlow using the Datastates API. It's just the pipeline to feed images into the network. I have a folder full of these tagged sentiment images. So this is my TensorFlow graph right here in this cell. I made this pipeline, and then this is the magic part here where you initialize the pre-trained network, so VGG16 in this case. I know the synopsis of this talk said inception, but I didn't get to that yet. So we're using VGG16. Don't be disappointed. It's still a good architecture. And then I load them from disk right here, model path. And then I say I want to use this fully connected layer 6. So I freeze this graph. Now the second part of TensorFlow is actually pulling the pictures through. So typically when you think of working with neural nets, you think of training and back propagation, but there's also the important part, the forward propagation. So I'm using the network here. And I'm going to save all my image features to disk in a features.binary file. So I'm going to get a bunch of 4096 dimension floats, and I'm going to save them to disk. They're going to be my training set for my linear classifier. And then I just start the session here. And I say I want this fully connected layer 6, and I want the labels, and then I just write them to disk as a binary file. And I do it in batches of 32. So then, right here, I'm just testing that I can read them. So now I have this binary file on disk of the features for all my images, and then I just read them right here. So this is the label, negative, positive, negative, positive. And right here, I'm just taking the average of the vector. I could have printed it out too, just to show that they're different. So I have my data set now. Now let's visualize it. So I'm going to take this high dimensional feature set and project it down to 2 dimensions using TSNE, which is generally well accepted for visual dimensionality reduction. Standard package right here. get it down to 2 dimensions. Remove some outliers here. Plot it. So looking at that initially, so blue and yellow are negative and positive. Looking at it initially, I wasn't too happy. What is that? I can't get any structure out of that. So anyways, that is essentially what we got out of there. That's going to be hard to fit a classifier to, at least in 2 dimensions. So let's explore that a little bit more. And I need this. So this is a continuation of that notebook. I load those feature vectors from disk again. Here's what they are if you want to see a concrete example. They're just floating point numbers. It's very sparse. And I'm going to now fit a classifier to it. There's a small class imbalance. So I just do some upsampling, do some dimensionality reduction, do some dimensionality analysis. So this is something I was speaking to Tiago with a bit earlier. So this is the variance of the image features, essentially. So you can see that variance really drops off after 400, between 200 and 400. So I have this 4,096 dimensional feature vector. Do I need all that information? Does every dimension encode a lot of information? No, not at all. So we can ditch some of those. I just went for 600. 200 works well too. Standard stuff for linear classifier. And then I do a quick little grid search almost of different classifiers. Here's the results right here. Overall accuracy. I go with the RBF SVM, which got 74%. And here's the confusion matrix. So that shows that we fed a novel data set of human labeled sentiment images into, and they're Twitter images, they're really weird things, they're memes and everything, into a network trained on object data. And we were able to pull out some information. So it did good on the positive, did good on the negative. Have kind of some false positive problems here on the negative class, but it's a starting point at least. And to explore, maybe why we have these kind of false negatives here, we can look at the actual images we fed through the network. The same way we did with Amazon. So that's right here. So these are the Twitter sentiment images projected in 2 dimensions. And this is a harder task, I think, for the network to segment. So we can see here there's a flower cluster. There's some type of a beach cluster right here. There's a big fire cluster right here. I like this one right here. It shows kind of the power of the network. There's like a pachyderm cluster almost. There's a rhino, and then an elephant foot, and an elephant. I thought that was really interesting. So it shows kind of difficulty of the images. There's like a shack cluster right here, and a lot of faces in the middle. So I think doing the sentiment on this is a lot more difficult than just simple object analysis, but there's a start. Now for the next step of this, let's take it a step further and look at, instead of just using this as a feature extractor, let's actually fine-tune the network a little bit. Let's actually fine-tune those last layers. Let's use the good benchmarks we had for the weights, and let's try and update the distribution a little bit. So what we're going to do here is we're going to take the pre-trained network, then we're going to train it, but only the last few layers, like in this picture. We're only going to train the last fully connected layers on our sentiment data. So we're going to do back prop not on the whole network, but only on a few of them. Because like we learned, the first parts of the network are well trained, they generalize stuff pretty well. So we're going to learn sentiment on the last part of the network. And I have this running right now. So I started it before I started speaking to you, and hopefully it's done. Oh no, I didn't start it. But we can start it right now, and you can see that it converges very fast because it already has all of the examples before. It's like, however old you are, you've seen a lot of things in your life. It's easier to learn something new because you have past examples. So that's what this network does. So I'm here in TensorFlow. I'm on a computer with a GPU, and I'm going to train 10 epochs of my last few layers on those sentiment images I just showed you. We can see that the GPU is pumping away here, 100% utilization. And we should get an answer pretty soon, and you'll see that the accuracy is actually higher than our linear classifier we just made. And this is only on one epoch. While that's going, I could show you in my notebook that's already done it. And this is the same, so this example is pretty much the same as the pre-trained model. I just initialize it, get the graph ready. And then you can see here I train it on 10 iterations. Standard TensorFlow boilerplate. I check the accuracy. So you can see, what did we get on the other linear model? We got average 70-something%. So on this one, we get higher accuracy on the second epoch of training on the validation set. If we let it go 10 iterations, we get up to 82%. And we can see it's done right here now. So on the first iteration of this fine-tuning model, we get better accuracy than we did on the linear classifier. So, and then we get all the way to 82%. And overall, if we let the whole thing train, we can get over 83% overall accuracy on image sentiment analysis. So, and that's pretty compelling results for fine-tuning. And the final example I want to show you is really fun, I think. Maybe a lot of you have seen this from Google. Let me open it up here. I think I have it open now. Have any of you seen this? Anybody play with this? Google was promoting this a lot, evangelizing their client-side deep neural network training toolkit. No one's seen it? Okay, we'll play with it together. So basically, they're trying to promote this JavaScript toolkit that lets you access the GPU through the browser and train a network. So what it does is it has 3 training examples, 3 classes we're going to learn. We could learn this class, we could learn this class, and we learn this class. So we're going to train our network right now, and then it'll do live classification, and then I'll tell you how it works. So these blue stickies aren't on my laptop by coincidence. I put them there. So I'm going to train the first label with this orange sticky, so it'll learn to recognize that. So you can see it learned 20 examples, and I don't know why that cat's doing that, but it learned 20 examples of what this class is. Now the next one I'll do is this next class, I'll make this my hand. Okay, we got 20 examples of my hand. And the final one I'll do is my face. Okay, so now it's running. It's already doing inference, forward prop. You can see there's 100% confidence that it's my face. I'll put my hand here. Now it's 100% confident it's my hand. And now I'll put the sticky note. %% confidence, it's a sticky note. Now, you remember my first slide, I mentioned these convolutional nets need lots of examples to learn. How did this thing learn with 20 examples per class? Because it leveraged a pre-trained model. And I know because I looked at the source. It's open source. So what they did is they leveraged a pre-trained model on Imagenet called SqueezeNet. So like I mentioned, VGG, Inception, they're very big. The weights for a VGG, for example, are 500 megabytes. So just a lot of floating point numbers, 500 megabytes of them. This AlexNet, this SqueezeNet, and there's a bunch of architectures that are optimized for mobile, are a lot smaller, more efficient, but still have good performance characteristics. For example, the SqueezeNet's only 5 megabytes. So what they did is they took a SqueezeNet architecture, we pass our images through it, our training examples, it collects those feature vectors, and then on inference, so it does some type of averaging on them, so we have some type of representation of class A, B, and C. And then when we do the forward prop, like right now, it takes the feature vector of my image, and then it'll just do a nearest neighbor to what it already has. And then it classifies it. So. And this is also explored a long time ago in the AlexNet paper, like 2014, which is this little picture right here. It shows how you can do simple image search using the feature vectors taken from the image. This left column here is the input image, so they passed these images through the network, got the feature vector, and then they did nearest neighbor search, got the top 6 or so, and you could see it's compelling because these images are the same thing, but it's sophisticated. They're different orientation, they're skewed. There's an elephant from the side and an elephant from the front. from this reference images, which is in a different orientation. So there really is power here in these representations. The neural nets, the deep convolutional nets definitely pull out some semantic meaning. And either leveraging these through as feature extractors or fine-tuning them for your own purpose. The common use case is, Imagenet has 1,000 labels. Your data set, your use case might not have that many. For example, I did the example of sentiment analysis, which only had 2 class labels. You can modify the network to fit to your 2 class labels using fine-tuning. So I think it's advantageous to leverage these pre-trained networks. And then the last one I want to go over, and then we're done and we can do any questions if we want, is the Expedia example. I didn't get much chance to pull any pictures from this or anything interesting, so it's real quick at the end, but maybe you saw the Expedia tech talk that they did a bit ago, where they showed how they automated the decision making for the default photo on a hotel. So whenever we look at a hotel's landing page, it's not trivial which image to display first to the user. Like, for example, we don't want to show an ugly bathroom picture, so I think a lot of the times humans just choose these. So what they did is they curated a data set through crowdsourcing of images, and they had them rate them 1 through 5. So then they were able to pass those images through a pre-trained network and fit a regression on them, and then sort the images according to the ranking. So then they can automate the default image selection process. So if anything, I think I've showed all of you some interesting use cases for transfer learning applications, and hopefully all of you will be inspired in your own groups to explore these options a little more. I know some of us already have. I'm looking at that guy, and there's lots of cool applications for it. Yeah, that's it. Any questions? Thanks.
Nice talk, really cool.
Thank you.
Thank you. So my question is, what is the difference between using the features from the first fully connected layer of, for instance, the VGG, and the second one?
Yeah, I think we kind of touch on that here a little bit. So you can see as we get earlier in the network, the feature representations are more primitive. So you can see here from the cluster in subfigure C that it doesn't have much structure. There's just kind of madness here. However, if you take it later in the network, and if we think of it, as each layer learns more and more semantic meaning, more structured meaning, and then when you project it down to 2D, there is some structure. So the features lower in the network are more general, less specific, but if you go too low, there's not too much meaning. And that's also evidenced in this figure here, where we do a baseline against a model that's not deep. So you'll remember this example, this baseline we used. Jarrett et al. On the bottom, that's a fully functional convolutional neural architecture. However, it's not deep. It only had 2 layers. So deeper is better.
And if you only have 2 classes, so binary, something like that.
Like the sentiment example.
Like the sentiment example. Do you feel that still we need to have a deep architecture, or when we have less classes, it's fine to have less layers?
Well, I don't think the architecture, I don't think the number of classes is a factor in the depth of the network. The depth of the network learns the semantic meaning. So whether you have 2 classes or 1,000 classes is irrelevant. So the depth of the network pulls out the features. And from there, the number of classes you predict is just up to you. Yeah, so I think they're independent of each other.
Okay.
So my question is that, is it necessary to have 1,000 features at the last layer? Or is it enough to have less? I mean, what is the correlation, or what is the relationship between the number of features at the end and the accuracy of the algorithm? Actually, the slide was perfect.
Yeah.
So did you manage to, have you measured this relationship? And I'm just interested in what is a reasonable number of features at the output. Is it required to have 1,000 or 150 is enough?
And I think maybe it's not even that complicated. The reason why all of these examples always have 1,000 labels at the end is just a product of it being trained on Imagenet, where you only have 1,000 class labels. So when this project was organized, when it was curated, The training examples only had 1,000 classes, so there's not really a scientific reason behind that that I know. Just a product of the competition that was driving all this research. So yeah, 1,000, as far as I know, is arbitrary. And we could look in the background here. It looks like our network's at 10 iterations, and it's at 83% on the validation set.
Just to repeat that example that you saw with the Google that we just trained the neural network. So there, you're saying that now to classify, it takes you a picture again, gets a feature vector, and then just does KNN to.
Some type of Euclidean distance, nearest neighbor, who knows? Yeah.
So it's not using the output of the neural network to classify. It's using then another algorithm.
It is using the output. Right now, the picture of me is going feed forward to the network. It's getting its feature vector, 4,000 dimensions, whatever the architecture is, and then it's comparing that to what it has already in memory.
So I mean, it's not like. So we were not doing the fine tuning. If I understand correctly, is something like, okay, now instead of having 1,000 classes, we just want two, in this case, 3 classes, right?
So yeah, there's 2 examples I talked about: feature extraction and fine tuning. This
Exactly,
is feature
yeah,
extraction.
yeah.
This isn't fine tuning yet.
Yeah.
There's no live training going on here. Yeah.
Okay.
But it highlights some interesting characteristics of transfer linking. Particularly, you can add a new class with only a handful of examples. It's pretty powerful, I think.
Yeah, exactly.
And all of this came from the great time and money put into the Imagenet project. So I think that's no small statement or exaggeration to say that the Imagenet project revolutionized at least research into AI. Yeah.
So again, sorry. When you first trained, you put that image as an input, and you put 20 images.
Yeah.
Was there a train there? What was the train there then?
It was, what was it trained on?
Yeah. Then we didn't train. We just extract feature vectors, right?
No training at all.
There was no training at all.
Yeah.
Okay. Yeah. Okay.
Yep.
Cool.
It's just comparing 2 vectors.
Okay.
The current one and the trained one. Yeah. Not even trained. I shouldn't use that word. The stored one.
You spoke about fine-tuning and feature extraction 2 ways. Is it also a common practice to use both for particular use case, or you have some kind of best practice as a rule of thumb? When should you be using fine-tuning? When should you be using feature?
Yeah. Karpathy, who's a very famous researcher in AI who's taught at Stanford and is now the head of computer vision at Uber, summarized it best in his slide that I stole. So good rule of thumb here. So the first column here is just a standard convolutional net. Then he says here, on the second column, it says, if your data set's small, fix all the weights, treat the CNN as a feature extractor, and then retrain a linear classifier on the end. That's like the example I showed for the sentiment in 2D. I retrained a classifier on that. So the rule of thumb is if you have a small data set, maybe just feed that through the network, use it as a feature extractor. But if you have a medium-sized data set, like my sentiment data set, on the second example, you can also fine-tune it too.
Don't you think apart from the size of the data set, the similarity also affects this decision? Like how similar is your data set with the data set on which pre-trained model was used?
Definitely, I think that's a consideration too, and I might even mention it here. Yeah, if your domain is completely different, you would have advantage even training the network over again or backpropping on the whole network. So instead of just backpropping on the last few layers, maybe backprop a little bit higher because if it is fundamentally different. And you would think that looking at we showed the example of the sun data set where it's just landscapes. Even without, this was just straight feature extraction, it still had some clustering too. So you'd have to have a pretty extreme data set to have to, I think, backprop on the whole thing again. Yeah. But yeah, lots of trade-offs and things to consider when you have a very variant data set from the source it was trained on. Yeah.
Thanks.
So when you're doing the fine-tuning, you just replace the last layer, so the softmax layer or something.
Yeah, typically you can go even higher, like in this example, any number of layers. Like this is, typically you just do the last fully connected, but you can even go higher too. I think also.
Yeah, but then it means more times of training to converge, I guess. More.
Yeah, definitely. Yeah, if you're doing, back propagation takes time, like I showed
Yeah.
on the first slide, it takes almost 2 seconds. I could do like two images a second. Yeah, the deeper you go, the more computation penalty you'll incur.
Yeah.
And that was the whole incentive not to train convolutional nets because they take a lot of power. So yeah,
And can you go back to the slide with the Tisni?
like this one.
No, the one with the different layers, in different layers, the one that you showed me. Yeah. So my question actually was also here you are giving an example of the first fully connected, right?
This example.
No, the right one. Yeah.
Yeah, the first fully connected. Yeah.
What do you find any difference between that one and the other one, fully connected?
Yeah, it's not explored on this one, but on some of the other examples, it is explored, and the results are generally lower. So, fully connected 7 versus fully connected 6, they're pretty close, but 6 always seems to eke it out better, I think, because it's a little more general. This one's a little specific to ImageNet. This one generalizes a little bit more.
Ah.
And you can make an argument. You keep going back, more general.
Yeah, of course, yeah.
Shapes.
But I guess if you want to keep the
And
labels,
yeah.
then the further you are in the network, the better. So if you want to keep this difference between a lake and a river, for instance, or
yeah, that's something you have to do something called abulation studies on, and there's a few papers that do that. There's one by Campos, if you want to look that up. Campos et al. Like 2015, they do abulation study on all the layers to figure out, which one is best. It's almost like a task you'll have to do to figure out what best fits your task at hand, which layer generalizes the best. And you can do that. You fit a classifier on each layer and do an evaluation on that.
Cool. Any more questions? No? Let me see. Okay. Remote questions? I guess not. Anyway, I guess then you can speak afterwards. Thank you very much,
Thanks.
Alex.